Okay. So far we have the following, right. So, we have u in Rn, and now we are saying we have to set up some transformation, linear transformation, which is something like 1 by square root k r, where r is just, every entry of r is a standard Gaussian, and we get mu, which is in rk, because r is in k cross n. Sorry, u is in d dimension, I should not say n. So, from d dimension, r is in, let me say, r is in k cross d, so that we end up with in k dimension. And we know that, basically what we know is norm of mu squared is a good estimator for norm of u squared. In fact, it is not too hard to show this is also an unbiased estimator. If you are interested, you should try showing this, right. So, the expected value of this value norm of mu squared is actually norm u squared. We will see if needed, we will show that later. Okay. So, how good is this estimate? That is what we care about, right, because we want to preserve lengths after doing this transformation, and then we are asking how good is this estimate, right. So, let's try to understand this question now. Okay. So, for this let's do the following. So, let's fix some u. Let's fix u in Rd, some u. Let's fix that. Now, let's say after I do this transformation, I get 1 by square root k r times u, and I get a vector in Rk, and let's call that vector v, where vi, the I, so this is a k dimensional vector, and the ith component of this is just going to be 1 by square root k ri transpose u, which is just sum over j equals 1 to d rij uj. Now, it is not too hard, right. So, to show that the expected value of norm v squared is just u squared. This is essentially the unbiased nature of this estimate. So, so take this as an exercise. Try to argue that the expected value of norm v squared is actually norm u squared, right. So, we pretty much did most of these calculations already, but you just have to write down this expression and square it, and then use properties of independence of Gaussian, fact that it's a Gaussian's variance is 1, mean is 0, and then you will get this basically, right. So, essentially what we are saying is that after I do this map, on an average the length is exactly the same. Now, contrast this with what we had originally dismissed as impossible, right. So, we said that there is you cannot have a rectangular matrix of dimension k cross d, where d is much larger than k, and then you multiply it with d dimensional vector to get a k dimensional vector such that the lengths match. That is impossible. No rectangular matrix can achieve this. But what we are saying is that if the rectangular matrix is Gaussian, scaled by square root of k, then of course the length is not going to match. For any specific instance of the Gaussian, it is not going to match. But if I repeat the experiment infinite times, then the lengths are going to match, right. So, the expected value of norm v squared is exactly norm u squared, right. So, which means that on an average, if I do the same experiment multiple times, then I will preserve lengths. Of course, in practice we are not going to do that, right. So, we are just going to do it once, but it's good to have this property that the estimator for the norm u squared, which is norm v squared, is unbiased, right. So, that is, if I do it multiple times, if I had the power to do this experiment multiple times and average it, I will get a good guess for norm u squared. I am not doing it, I am just doing it once. So, which means that I need to worry about, because I am doing it only once, I want to understand how far away is this guy, right. So, I want to understand the chance that when I do this once, the chance that if I measure the length after I do the transformation is too far away for my comfort level than which is 1 plus epsilon times norm u squared, right. So, I want to understand this probability. So, let's look at what is the question that we are asking. We are saying that this is the length of a vector in n dimension, right. So, this is in n dimension, this is in k dimension. V comes of course using 1 by square root k r times u, and then I want to ask the question, when I do this, when I take a random matrix R, scale it by square root k and then apply it to u and get V and then measure V's length, I know if I repeat this experiment infinite times, I will get back, and then average it, I will get back u's length squared. But if I do it once, what is the chance that the length of V squared is greater than or equal to 1 plus epsilon times norm u squared? That is, what is the chance that something can go wrong? Because I want the length to be preserved to 1 plus epsilon. I want norm V squared to be less than or equal to 1 plus epsilon times norm u squared. So, which means that I want to ask the question, is this a common event or a rare event? If it is a rare event, then the chance that something that I do not want to happen, which is the norm of V squared is greater than or equal to 1 plus epsilon norm u squared. So, this is the bad event for us, right. So, this is the bad event. Why is it bad? Because when this happens, I am not preserving lengths to 1 plus epsilon accuracy, right. So, something bad is happening. I want to know with what probability something bad will happen. That is the question that I am asking, right. So, can I bound the probability of something bad happening, right. So that is what we want to analyze now, right. So, let's try to analyze that. Let's see how to get that, right. So, now u is a fixed vector, there is nothing random about u, it is a fixed vector. V is random because R is the matrix R by square root k is random, but what we are going to do is we are going to slightly change things so that we get a slightly more handle on this problem, on the randomness of on the random variables that we are operating on, right. So, for this we are going to define, and we will see in a minute why this definition makes sense. We are going to define a new vector x, which is just, I will define it and then we will talk about why this definition makes sense. I am going to define it as square root of k times V divided by norm u. It might seem arbitrary by now at this point, but we will see why this is an useful thing to consider. Remember, again I keep repeating, V is in Rk, right. So, in fact V itself is 1 by square root k Ru, right. So, let us not forget this. This is just V, and then in some sense I am kind of normalizing things in this way when I say I am multiplying it by square root of k and dividing by norm of u. We will see in what exact sense in a bit, right. So, this is my x. Now, what is the first thing? What is the length of x squared? Well, this is just the length of square root k V by norm u squared, which is square root k squared is k, norm u squared is a constant that is squared, and then this is norm V squared. So, the length of x squared is just k times norm V squared by norm u squared. So, somehow I mean the x squared has all the ingredients here, right. So, it has k, it has norm V, it has norm u squared also, right. So, somehow when we want to make a statement about this probability, it involves norm V squared, norm u squared. I mean, we will see that things simplify when we use x because it already has norm V squared divided by norm u squared. I will come to that in a minute. So, this is one. Now, so this is also a random quantity. Why is this random quantity? Because it is just some scaling of V, right. So, V is random because R is random, U is fixed, R is random, so V is random. I am just scaling V, so X is also random. So, now let us ask what is the expected value of X? Well, what exactly is X, right. So, X, what are the components of X? So, this is just the expected value of, well, every component of v is scaled by square root of k by norm u. What is the first component of v itself? Well, v is 1 by square root k r u, which is just 1 by square root k r1 transpose u dot 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 square root of k by norm u 1 by square root k r k transpose u, which is just the expected value of 1 by square root u r1 transpose u dot 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 1 by square root u r k transpose u. But then this is just a scaling factor. Expected value of r1 transpose u we already know is just 0, right. So, which means each of these components expectation is 0, which means that this is just a 0 vector, right. So, this is just 0, that is a vector 0. So, expected value of x is 0. Now, remember this is a vector, right. So, it is a k dimensional vector. Now, I can ask, how does the covariance matrix of this vector look like? Well, if it is a number, we will ask about variance, mean and variance. If it is a vector, then we will ask about the expected vector, mean vector, which in this case is 0, and now I am asking about the covariance. So, let's ask the covariance about the diagonal entries first. For any II, right, so the ith diagonal entry, so covariance, remember the covariance is a, in what dimension, because this is x is a k dimensional vector, which is just a scaled version of v. It is also a k dimensional vector. So, the covariance is going to be a k cross k matrix, right. So, now I am asking, let's observe the diagonal entries of this covariance matrix. So, what would that be? Well, that would be just the so the expected value of, you know, the square of the entries. So, what entry do we have? Well, the entry that we have is square root of k by norm u into 1 by square root k r1 transpose u the whole squared, and so on. So, the ith entry would be ri. So, this would be the ith entry, I comma I entry of the covariance matrix. So, this gets cancelled. So, this is just expected value of r1 transpose u squared by norm u squared, but we already argued the expected value of r1 transpose u squared is in fact norm u squared. So, this is norm u squared by norm u squared. So, this is just 1, and so which means that the diagonal entries of this covariance matrix are all 1. Now, what about the off diagonal entries? Well, if I look at the off diagonal entries, if I take any ij, I not equals j, so then that is going to be the product of those two entries, expected value of the product, which is k by norm u 1 by square root k r1 transpose u into square root of k by norm u 1 by square root k, rj transpose u. This cancels. So, I have 1 by norm u squared expected value of ri transpose u into rj transpose u. Well, but ri transpose u and rj transpose u are completely independent random variables with mean 0 and variance norm u squared. So, because they are independent, now the product of expected value of their product is the product of their expectation, and each of their expectation is just 0. So, this whole thing is just 0, right. So, which means the covariance matrix is diagonals are all 1, everything else is 0, which means the covariance matrix is just the identity matrix, right. So, in k dimension, k cross k. So, then what are we saying? We are saying that so just to just so that we are on the same page, right. So, you started with u, which is in Rn, and then I applied 1 by square root k r to it to get v, which is 1 by square root k r u, and then I am doing some scaling to get x, which is just square root k by norm u times v. Now, what I am saying is that this x, expected value of x is 0 vector, and then the covariance of x is just the identity in k cross k. Basically, then what we are saying is that the x vector is just a standard multinomial random variable, right. So, x is a standard multinormal, multidimensional, or rather multivariate normal variable, right. So, which is x is distributed as Gaussian with 0 mean, mean vector, and then identity matrix in k cross k, which is interesting. The reason why this is interesting is because we know a lot of properties about standard normal variables, multivariate normal variables, as opposed to properties about v or u. We have much more control over x, right. So, of course, v is just a scaled version of x, but still it is easy to talk in terms of standard normal variables, and that is why we are just using x for no other reason, because later we will use some properties of multivariate normal variables to do our analysis, to get a hold on the probability that we care about, and so talking in terms of x is easier than in terms of v and u. So, let's use this now, right. So, this is one property of x that we have. The other property, if you remember, is that is the following, that we had put down earlier, that norm of x squared is just k times norm of v squared by norm of u squared. This is true for irrespective of randomness, that just comes from the scaling. So, that is also a property. So, now what did we want really, right. So, now let us go back and ask what we really wanted. We want a hold on the probability that after I do the mapping from u to v and I want to understand the chance of the bad event happening, I somehow want to hope that the chance that a bad event happens is small, right. So, it means with small probability something can go wrong, but most of the times the length is preserved up to a factor of 1 plus epsilon. That's the hope that I have, right. So, and let us see if that hope is true or not, right. So, for that now we will rewrite this guy in terms of x. So, because we know norm x squared is k norm v squared by u squared, I can rewrite this. This is exactly same as I am asking a question about the probability of norm x squared is greater than 1 plus epsilon times k, right. And why is this true? Because if I write it as so let me actually write it this way. So, this is equivalent to saying norm v squared by norm u squared is greater than or equal to 1 plus epsilon, which is equivalent to saying that probability that k times norm v squared by norm u squared is greater than or equal to k times 1 plus epsilon. This is just a rewriting. Now, if this event happens, well, if norm v squared by norm u squared is greater than 1 plus epsilon, if that event happens, then of course, k times norm v squared by norm u squared will be greater than or equal to k times 1 plus epsilon. So, the probability of these two are the same, but then this guy is just our norm x squared, right. So, this is just a multivariate normal random variable. So, this is just probability of norm x squared greater than or equal to k into 1 plus epsilon. So, essentially then what we have reduced the problem to is something super simple now, right. So, now we are saying that, and let me state the English statement, and then we will talk about how to get the final answer next time. But essentially in all the discussion that we have done so far, if we have to summarize that, this is what it is, right. So, I have a vector u in d dimension, high dimension. I am mapping it to k dimension, and I want to know something bad happens. What is bad? The length squared of the vector in low dimension is greater than 1 plus epsilon times the length squared of the original vector. This is a bad event that might happen. I want to understand with what probability such a bad event happens. With all our analysis, we have reduced it to saying that you can either study that property or you can study something much simpler, perhaps something much simpler, which is the chance that a bad event happens is exactly same as the chance that if I generate a random Gaussian vector in k dimension using a standard multivariate Gaussian vector in k dimension with mean 0 and variance the identity matrix, and I measure its length, the length is greater than or equal to k times 1 plus epsilon. Now, the chance of this is exactly the same chance that, if I start with u, I map it to v, and then the length of v squared is greater than or equal to 1 plus epsilon times the length of u squared, right. So, of course, we have to study separately the chance that it is smaller than what we need. The argument is exactly equivalent to that. So, we will do this argument and then that will follow along similar lines. But then the interesting thing is that now the chance that we really care about has been completely reduced to a question about a random vector in k dimension, right. So, where k is involved, where epsilon is involved, right. So, there is no involvement of d, and that's the brilliant thing here, right. So, we started with some d-dimensional vector, but then eventually is saying that the chance of a bad event happening can be understood if we somehow have a handle on generating a random k dimensional vector and then asking what is its length, and if can it have a large length, right. So, a length which is greater than k into 1 plus epsilon. If we understand this, then we understand our original problem. Now, how do we understand this? We will see that next time. So, that needs some understanding, some properties of multivariate standard normal variables, which I will state. We won't prove some of these properties, but then we will try to analyze this. We will use all the machinery that we have built so far. We will use Markov inequalities, we will use union bounds, we will use everything that we have seen so far to answer this question. And if we somehow manage to show that this probability is small using all the tools and techniques that we have, then we have hit jackpot, because then we have a way to transform any high dimensional vector to a low dimensional vector such that the lengths are approximately preserved with very high probability. Well, does that happen? Well, of course, we know the answer that it happens. That's what JL lemma says. But how can we convince ourselves that it happens? Well, we will have to look at this probability, which is something that we will come back next time and analyze. Thank you.